Hello, so in this video, we're going to talk about ASCII and Unicode, which are very fundamental and very important concepts in computer science and for programming in general. Okay, so just a little bit of background information. So probably many of you have heard that the way that computer stores informations are in ones and zeros. Right? Those are called bits or um, the bits stand for binary digits. So there's the ones and zeros, and this kind of constitute a what's called a binary system. It's kind of just like the decimal system that we're used to, but it's binary because it only has zeros and ones, and or the fundamental units are zeros and ones. So for example, if you have 8 bits and eight basically 8 zeros or ones, um, to represent the number 0, we use all zeros, or 8 zeros, and then to represent the number 1, it's 0, 0 all the way to 1, and then to represent 2, it's 1, 0, 3 is 1, 1, and so on and so forth. Exactly how that works, we're not going to get into that right now or in this course. But this is kind of just the basic idea. It's a combination of zeros and ones, and they can represent different numbers. However, not all the information can be represented by just numbers, right? There are a whole lot of information that are stored in languages, alphabets, right? The entire Shakespeare, all his plays are mostly just written in the English language, so they are stored as alphabets or characters. So then the question is, how in a binary system do you store characters in addition to numbers? So that's what the computer engineers, they come up with the idea that certain bit patterns would represent characters. Now they can also represent numbers at the same time, but depending on how we want to interpret those bit patterns, they can either represent numbers or letters or characters. So for example, this bit pattern 1 0 0 0 0 0 1, that if you do kind of the math, if you know how to convert binary numbers into a decimal number, is the number 65. But the computer engineers, or from the early days, they also decide that that number also maps to a character capital A. And then the number 66 maps to a character the capital B, 67 maps to capital C, and so on and so forth. Okay, so this is the system they come up with. Now, this kind of mapping, it really has to be standardized, meaning you cannot have one system that does this and then there's a system that maps, let's say, do it in a different way. Let's say a different system that maps 65 to, I don't know, this small a or the letter Z or some other random characters, right? If you have system that represents characters in a different way, then you cannot interchange. You cannot exchange information between these systems. So that's how they come up with a standard, and it's called ASCII, and it's short for American Standard Code for Information Exchange. And this is the standard that they come up with. So this is just a small ASCII table. The entire ASCII table looks like this. Okay, so the way to read it is there are many columns, and the most important columns are the first column, which is the decimal number. Okay, and then the last column, which is the character. Now, there are lots of non-printable characters. The ones that we mostly care about are the printable ones, such as all the alphabets, right? All the capital letters and small letters. Excuse me. So if you look at the number that represents capital A is 65, and that's the capital A, And then if you look at the number that represents or that maps to the small a, that is 97, and you can just go down the table and figure out pretty much for all the characters what their equivalent or what number they actually map to. Okay, so again, yeah, these are the English alphabets in this table. Now, how do we work with ASCII code and characters in programming in general and in Python in particular? So the most often operation that we have to do that has anything to do with ASCII code is how to convert from character to ASCII and how to convert from ASCII to character. And the way to do that is to convert a character to ASCII code. We use a built-in function called ORD. I believe that stands for ordinal. ORDINAL, ordinal. Okay, so that's basically a number that gives you it basically, given a character, it gives you the number or the ASCII code that represents that character. And going the other way is, given an ASCII code, given a number, we can convert it back to a character by using the built-in function character, CHR. Okay, and to see that in action, I have typed that up. So this is basically the same code. I'm converting the capital letter A to its ASCII number, and I'm printing it out. And I also do the other way. I have a code, I have a number, let's say 100, and I want to convert it back to a character. So let's run this. And basically, yeah, it shows what you expect. You know, the capital A is the ASCII code is 65, and then 100 is D, which is 100 is a D here. Okay, so you can obviously change this around. You can say B, and then B is 66, C is 67, and so on. Okay. All right. So now maybe it's time for you to give this a try. Now, note that the character 0, okay, this is the character 0 because it's in quote, right? It's not the same as the number 0. So the character 0 is not mapped to ASCII code 0. So can you write a short piece of code and find the ASCII code for the character 0? And once you do that, you know, try to change it to 1, 2, 3, and 4, and try to figure out, you know, the number that maps, that the character, that the digits, sorry. So try to find the ASCII code that all the digits map to. Okay, so pause the video and give this a try. Now, assuming you've done that, it means you basically do exactly the same thing as what I did here. But here is part of the ASCII table that maps the character 0 to the number or the ASCII code 48, and the character 1 maps to ASCII code 49, so on and so forth. So if you did everything right, this is what you should come up with. And know that, yeah, there are other characters and they all have ASCII code mapping, such as parentheses, quotes, spaces, colons, etc., etc. Okay. Now, why do we care about the character, the conversion between characters and ASCII codes? There are actually many uses for that. So one example is how do we convert a lowercase character into their uppercase equivalent, such as how do I convert a lowercase a to an uppercase A? So given what we have done here and given the ASCII table, you should be able to figure a way to do that. So I'm going to give you a chance to think about it before I show you the answer. Okay, so what it is that you really want what you need. The important ingredient to this kind of puzzle is that the ASCII code for the lowercase characters, such as just small a, is always 32 larger than their uppercase equivalents. So small a, 97, is 32 bigger than 65, the capital A. And then the small b, which is 98, is 32 larger than capital B, which is 66. So we use that observation and that kind of rule, and we can very easily convert a lowercase character into an uppercase character. And the way to do it is, hopefully you kind of figured this out already, and that is I'll first convert the character into its ASCII equivalent, right, using ordinal, and then I subtract 32. Now, this gives me a number. I subtract 32 from the number, and then I convert that number back to the character. Okay? And so that's what I did here, and I'll show you how that works. Okay, so you run this. I'm trying to convert A to the uppercase A, and there, upper of the lower character of character is yeah, small a capitalizes, the big A, right? So if you change this to, I don't know, another character, let's say Z, Z is, that small z gets converted to bigger Z, okay? Or upper capitalized Z. Anyway, okay, I hope that makes sense. Now, having done this already, because this is such a frequent operation, I mean, Python, being the all-powerful language that it is, it already has a built-in facility to do this. And so you can just give it a character. You can do a dot and upper. And then this method will convert this character into its uppercase equivalent. So we can do this. Oops. Okay. And this is basically just using upper. And yeah, it will just do that for you. Okay. So yeah, so then you ask, okay, why do we care if Python's already doing this for me? Well, we care because, well, this is how Python, the upper, basically works. It basically just takes the ordinal of that character and it subtracts 32 from it, and that's how it does conversion. So it's employing the same exact idea that we now understand, right? And also, this is important for other potential use cases for characters. Okay. Now, ASCII is unfortunately not enough. That was because when ASCII was standardized, that was a long time ago. I don't even remember which year was that, but it was a long time ago. And back then, the languages used in computer is basically just English. So that's why ASCII, if you look at the ASCII table, it only has English characters and other, punctuation marks and stuff like that. But the language, the alphabets that's here is just the English alphabets. So its limitation is that it only uses 8 bits. Well, really just 7 bits if you look at the ASCII table carefully. So it can only really map up to 128 characters. And obviously that's enough, that was enough for English, but if you go to other languages, especially the Far Eastern languages such as Chinese, Japanese, Koreans, they have many, many, many more characters, and 8-bit is simply not enough. So at some point, it was recognized that ASCII is just not enough. So we need a bigger space to store, to map all the characters to numbers. So, and that's when Unicode was invented. Now, one good thing about Unicode is it's totally backward compatible with ASCII. So the first 128 numbers in Unicode maps to the exact same English characters in Unicode. And Unicode is also very flexible, very extendable, I would say. It allows for a number of different encoding schemes. So there are even different ways to encode Unicode. So Unicode is not a single schema. The most common one is called UTF-8, I think. That's what I use mostly at work. And regardless of what the encoding schemes are, Unicode just use more bits, more than 8 bits to do the character mapping. So it's able to store pretty much all the characters in all the languages in the world. And I have, so before I say that, I believe Python 3 by default use UTF-8 for all of its encoding. And at least on my system, that's the case. And you can actually figure that out by doing this funky little 2 lines of code. You import the system. Sys, as we've seen, kind of very useful, tells you a lot about the system, and you can do a system sysget default encoding. And on my system, it says UTF-8 basically. So that's why I think Python 3, at least on the Mac, the default encoding is UTF-8. And also, to show you that it actually represents non-English alphabets, so this is a Chinese character, okay, and the good thing is what we just say about the ordinal and character conversion. It works exactly the same way as they did for ASCII. As a matter of fact, I think these are written from the ground up to handle Unicode. And the fact that it happens to work for ASCII is just because, again, Unicode is backward compatible with ASCII. So if again, this is a Chinese character here, and if you want to find out the Unicode for this Chinese character, you do ordinal, you run it, and the Unicode for that is 20,013, which, as you know, is a much bigger number than 128. So this cannot be stored in an 8-bit system. But again, because Unicode uses many more bits, it's able to store characters, and then the conversion the other way around, you're converting 20,013, it converts back to this Chinese character here. Okay, so that's all I want to say about ASCII and Unicode.